Alright, today we're going to do a Discrete Mathematics 1 midterm that I have at TrevTutor.com in the Discrete Math 1 section. So this is the first midterm. This will cover set theory, logic, and counting. There's already a written solution up on the website, but I figure for explanation purposes, it's probably good to do a video on this. So the questions are based off my videos, and a free textbook online that you can type in the book of proof into Google, and you can find that book online. So some of the questions are directly out of there, and some are made up. So, 70 points. Let's go. So here's some basic set theory. Suppose A is the set ABCD, and B is the set 1, 2. We want to write out some sets here. So what is A cross B? Well, A cross B is the set where we have a bunch of ordered pairs. So in each ordered pair, the first number is going to come from set A, or the first element is going to come from set A, and the second element is going to come from set 1. And these are going to be all the combinations. So we have A1, A2, B1, B2, then we'll get C1, C2, and then we'll get D1 and D2. So there's a lot of different elements here to write out, and it looks kind of messy, but it's just the cross product. Okay, A union B is all the elements of A and all the elements of B. So we get the set A, B, C, D from A, and then all the ones from B, so 1 and 2. Okay, what is A intersection B? Well, these are the elements that are in both sets. So what's in both sets? Right, there's nothing in both sets. So this is just the empty set, which can be written as this. So what is B minus A? Okay, well, we take all the elements in B, 1 and 2, and then we'd subtract all the elements in A. So we're going to remove A, B, C, and D from 1 and 2, and we're just going to be left with 1 and 2. Because A, B, C, and D are not in B, so we don't need to worry about it. Okay, what is the power set of B? Okay, the power set is the set of all possible subsets. So let's remind ourselves that B is the set 1 and 2. So the power set of B, which I wrote like this in the videos, so hopefully the symbols weren't too difficult to discern, but that is going to be, first of all, it's the set, the empty set is a possible subset of B. The set containing 1 is a possible subset of B. The set containing 2 is a possible subset. And the set containing 1 and 2 is a possible subset. So remember, the power set is just the set of all possible subsets. So the empty set containing 1, set containing 2, and the set containing 1 and 2. To be sure, we say, okay, well, the cardinality of P to the B should be the same as 2 to the power of the cardinality of B, which is just equal to 2 to the 2, which is 4. And we see that, yeah, the cardinality of power set of B is 4, so we should be good. So that was question 1. A nice, easy question to start things off. And then we go into something a little bit harder, which is saying, prove the following statement. We want not A union B is equivalent to not A intersection not B. Okay, well, we need to do two things. We need to prove that A union B bar is a subset of A bar intersection B bar. So let's do this step first. Okay, we're going to say that X is an element of A or B bar. So we're taking some random element X, and we're just saying, okay, well, we know X is in there. So we want to prove that X is also in A bar intersection B bar. So that means that X is not going to be an element of A union B. Okay, so if X isn't in A or B, then we know that X is not in A, and we know that X is not going to be in B. Which means that x is going to be in A bar and x is going to be in B bar. So we know that x is going to be in A bar intersection B bar. So because x is in A union B bar, x is going to be in A bar intersection B bar. So that is one way. The second way, we have to show that A bar intersection B bar is a subset of A union B bar. So we take x as an element of A bar intersection B bar, and we pretty much go the opposite way. So we know that x is in A bar and x is in B bar, so x is not going to be in A and x is not going to be in B. Therefore, we can claim that x is not going to be in A union B. Therefore, x is going to be in A union B bar. So this is just taking an arbitrary element and messing around with English words and logic to figure out that the following conclusion can be made. So because A union B bar is a subset of A bar intersection B bar, and A bar intersection B bar is a subset of A union B bar, then we can conclude now that A union B bar is equivalent to A bar intersection B bar. So a little bit more confusing. If you were to just use set laws, then like if you were to say, oh, okay, well, we have A union B bar, and then by De Morgan's, we have A bar intersection B bar by De Morgan's, then you would have got 2.5 out of 5, because it's not a proof. That is a set theoretical proof. Well, not even a set theoretical. That is a set theory proof that hasn't really been formally explained, because this step right here where you say by De Morgan's, that's the whole point of the proof, is to prove that De Morgan's works. So just writing this down is kind of like saying, well, at least you understand what you're supposed to do, sort of. So give you half a mark for that. And here's a cool question I made up because I like it. We're going to prove that A minus B is equal to A intersection B bar using Venn diagrams. So let's draw two Venn diagrams. So probably some of the nicest rectangles I've ever drawn on this series. So our left one's going to be A minus B, and our right one's going to be A intersection B bar. So let's draw our circles in there. Of course, I'm sure I'll butcher these circles and make it look kind of ugly. Okay, well, not too bad. We'll fix this one. This will be A, this will be B, this will be A, this will be B. On the left side, it says that we want everything in A that's not in B. So we just end up with this area. On the right side, we want A intersection B bar. So A is this whole lovely area here. And not B is everything outside of B. So we get some crosses here. And we don't go inside B, but we cover everything else. And we see that all of the overlap is right in this section here. So this is the same area as A minus B. So why a Venn diagram proof? That's to show that you visually know what's going on. This is a very easy definition to memorize, but do you know why graphically it works? So it's a nice way to test to make sure you know what's going on visually. All right. Question number 4, we start to get into logic. So that was all of set theory. Now with logic, we have some sentences here, and I just ask you to state whether they're statements. So if it is a statement, you don't have to say whether it's true or false. You don't need to say why it's a statement, but we'll go over this one by one and I'll explain the answer. So it is currently sunny outside. Yes, that is a statement because that could be true or false. It is sunny outside. Yeah, it's true. It is not sunny outside. That's fine. What about it can't possibly be raining, can it? A little typo there. Well, this is a question. You're asking a question here, so No, it's not a statement because it's a question. Statements are declarative sentences. They are facts that could be true or false. If I say, it can't possibly raining, can it? And I say, yeah, that statement's true. What does that mean? I have no idea what that means. It doesn't make sense. So that's not a statement. Question C, every even integer is of the form 2n plus 1. This is a statement. This is a false statement. And the reason I put this question on is because this might trip you up because you're saying, hold on, even integers are not of the form 2n plus 1. But doesn't matter because it's a statement. I'm not asking whether the statement is true or false. I'm asking what statements are. So that's why this question is on there, so that way you know what I'm asking and you're answering the right question. Okay, question D, this is really tricky. I felt bad for this actually, because when I wrote this question, I wrote it intending this to not be a statement, but it is a statement, and unintuitively, it might be a statement. So if I say, I hope you do well on this question, I'm making a statement about my feelings. You don't know whether it's true or false. You do not know if I hope you do well, and you really can never know. An outsider is not going to know whether this statement is true or false, but I do, therefore it's a statement. So when I wrote this, I was like, I need another question that's not a statement, and then I accidentally made a statement. So, kind of tricky. Here's the last one. This one is a dead giveaway because I started it with, it is a fact. So straight off, this is going to be a statement because it ends in a period, has no questions in it. But, it's a nice mind-tricky question. It is a fact that anyone who says this question is not a statement will be correct. Well, it is a statement, but I hope that by putting enough words in there and confusing your brains, you would spend more time thinking about the meaning of the sentence rather than the fact that it is just clearly a statement. So I did put two tricky questions in here. C and E, I tried to fool you, and D, I fooled myself, and, well, it's kind of tricky. So, would I expect you to get at least 3 out of 5? Yeah. Not too bad. Okay. Prove the following formulas are equivalent using a truth table. We have not P biconditional Q is the same thing as P arrow not Q and not Q arrow P. So, I'm going to do sort of an abbreviated truth table for this. So we have not P biconditional Q, that's going to be 1, and our second one is going to be P arrow not Q, should spread this out a little bit, and not Q arrow P. Okay, so I'm not going to do individual columns for P, not P, Q, not Q, so on, because it's really long. So instead, I'm going to write all the truth values right below what we're working with. So P's and Q's I'm going to do in dark blue to be consistent. So with all the Q's we're going to write 1, 0, 1, 0 below. All the P's will write 1, 1, 0, 0. And if you haven't seen this method before for truth tables, this is much more common in philosophy and, in my opinion, is a lot better. It doesn't take up as much space, it's more intuitive. So okay, we'll do red for negation. So now we're going to deal with all of the negations. So not P is just the opposite values of P. So we change the values of P from 1 to 0. So we have a not Q here, so that's like that, and we have a not Q here, so we will get this sort of rating. Now, what we can do if we want is we can just erase the columns where we have P, but for the sake of keeping everything there, I will not erase them. So now, when we deal with this biconditional next, we'll use green for this. Actually, no, we won't because that's difficult to see. We'll use purple. Now we're going to look at these two columns. So, is 0 the same as 1? No. Is 0 the same as 0? Yes. Is 1 the same as 1? Yes. And is 1 the same as 0? No. So, the final answer here for this column is going to be 0, 1, 1, 0. So that's our main column. Now, when we do P arrow not Q, we're going to look at these two columns. So we know that P arrow whatever is going to be false only when P is a 1 and not Q is a 0. So we have a 1, 0 here, so this is going to be a 0. We have a 1, 1, so that's a 1, a 0, 0 is a 1, and a 0, 1 is a 1. Okay, so now we have our arrow for P arrow not Q. Okay, what about not Q arrow P? Well, it's going to be the same thing. We're going to deal with these two lines. So 0, 1 is going to give us a 1, 1, 1 will give us a 1, 0, 0 will give us a 1, and 1, 0 will give us a 0. So now we have our arrows. Okay, now let's work with our conjunction. So we're going to be looking at these two lines now. This is why I'm doing them in different colors so we know what we're working with. Okay, so we use the conjunction, so it's only true when both of these are 1s. So a 0 and a 1 will give us a 0, a 1 and a 1 will give us a 1, a 1 and a 1 will give us a 1, and a 1 and a 0 will give us a 0. So now we have our final row for this side. So these are the same, therefore these are equivalent. So this is a much, I'd say it's a nicer way of doing a truth table. It's a little bit harder to keep track of the rows you're doing, but all the information you need is literally right in front of you. So that's one way of doing a truth table. You can do it the same way you've done it before, where you do a column for P, then for Q, then not P, then not Q, then not P, biconditional Q. But if you do this, see, we already have 5 different columns going on, so it's probably nicer just to put it all in one big thing. That's just my opinion. So that was the first question in logic. The third question in logic is formalizing an argument. So I have this paragraph. Either Derek works or Avery does not work. If it is not true that both Avery works and Brandon does not work, then clearly Selena does not work. However, Derek does not work. So does Selena work? So our first step is to formalize the argument. So I very nicely made their names start with A, B, C, and D. So A is going to be Avery works. B is going to be Brandon works. C is going to be Selena works. And D is going to be Derek works. Okay, so this will be your first amount of points. It's either 2 or 3. I believe this is 2 points, what I have on the answer key. So that would be 2 points right there for formalizing it. Now, we have to take a look at our sentences here. So we have either Derek works or Avery does not work. So how do we formalize that? So Derek works or Avery does not work. So D or not A. The second sentence, if it is not true that both Avery works and Brandon does not work, then clearly Selena does not work. Okay, so if it is not true, okay, so we have a not, that both Avery works and Brandon does not work, then clearly Selena does not work. Okay, so the reason that we have not true that both is to say that this not basically covers A and not B. Because if I said if it is not true that Avery works and Brandon does not work, that would be ambiguous. So because we have it is not true that both Avery works and Brandon does not work, that means that we have this not encompassing the whole A and not B. So we have not A and not B, arrow not C, because clearly Selena does not work. And then for number 3 here, we have Derek does not work, so we have not D. So this right here would be 3 points to make sure you got the sentence right. Okay, and the next, we have to do some logical reasoning here. So we have to conclude something about Selena. Okay, so we have not D and D or not A, so we can get not A. So we get not A from 1 and 3, and disjunctive syllogism. So I might have called this something else. If I did call it something else in my video, just use whatever word you have for this operation. But when you have alpha or beta, and then you get not alpha, then at least alpha or beta has to be true. So we know alpha is not true, therefore it must be the case that beta. So we did the same thing here. We said D or not A. Well, not D, therefore it must be not A. So that's the form of the disjunctive syllogism. For our next step, well, we have not A, and we need to somehow get A and not B. Okay, well, we can use disjunction introduction to say, okay, well, what about not A or B? Because we can attach anything we want using disjunction introduction. So this will be 4, and I usually call this VE. So in an example, if we say, if we take alpha, and we have this truth table 1, 1, 0, 0, and we take alpha or beta, so we get 1, 1, 0, 0, 1, 0, 1, 0. What's going to happen is that, hold on a second, this will be 1, 1, 1, 0. So it's still going to be true in the same situations. So we're not going to get a contradiction here. So this is okay. So not alpha or beta, totally acceptable. And this does follow from the rules I showed in my logic laws. So at this point, we can do some De Morgans. We can say, okay, well, this is the same thing as not A and not B. So that's just De Morgans from 5. And because we have not A and not B, then from 2, using modus ponens, we can get not C. So that's going to be from 2 and 6, and modus ponens. So it's a little bit of a challenging proof. So the reasoning that you take to get there, as long as there's some sort of logical step, it's going to be 3 points. And for 2 points, you have to specifically write out Selena does not work. Because I did ask the question, does Selena work? So it has to be answered. So that's the breakdown for this question. Pretty straightforward logic question, has a bunch of sentences that has to be translated, then you have to do a proof and make a conclusion. So that's pretty much the most in-depth logic question you're going to get. So here's some questions about counting. This is probably the section that you're mainly watching for if you're doing this video, because I think this is probably the hardest section to at least wrap your mind around just through text. So suppose we have a committee of 15 people. How many ways can we select a president, vice president, and a secretary? Well, we have this president spot, so this will be our pres spot. So we have to select somebody out of the 15 people. So there's 15 choices for the president. And then for the vice president, well, we just picked one of those people to be president, so there's only 14 choices left for vice president. And then as far as the secretary goes, well, we selected one person for president and one person for vice president, so there's only going to be 13 people left for the secretary. Therefore, your answer is 15, 14, 13. Sorry, 15 times 14 times 13, which is some number that you don't have to compute. This is fine. Some people would say that this is 15p3 if you use that notation, where you have 15 items and you choose 3 for a permutation. I think that notation is really ugly, so 15 times 14 times 13, whatever you use to get that answer, that is correct. Okay. Suppose we have 150 people eating 150 people are eating a lottery. No, okay. 150 people are entering a lottery to win discrete mathematics textbooks. How many ways can we choose 5 winners? Well, we're choosing 5 winners, so clearly order does not matter here. So this is the same thing as 150 choose 5. Or, if you want it to be really snarky and crazy, you could say it's 150, choose 145, because we're choosing 145 losers. So either of those is acceptable. That one I think is probably the one you're definitely going to get if you've paid attention to any of the counting material. So here's a harder question. It's not really harder, it's just a little bit different than something you might expect. So suppose we have a binary strength of length 15. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Okay, cool. How many possible strings will have exactly 6 zeros? So what that means is that we take the 15 positions and we choose 6 of them to have zeros. So we could be like, okay, 1, 2, 3, 4, 5, 6. And then we just fill the rest of them with 1s. And there's a binary string of length 15 with 6 zeros. So equivalently, we could say it's just 15 spots and then we choose 9 of them to be 1s. So these two questions are nearly identical. I put these beside each other for 2 reasons. One, nobody expects me to ask the same type of question twice in a row. That's insane. Why would anybody do that? So I'm trying to mind trick you there. And 2, this might not be obvious for what the answer is. So it's kind of cool. I like it. I like this question because it's not tricky at all, but it kind of messes with your mind because you're thinking, hold on a second. Strings, we have to have exactly 6 of them zeros. How do we order these? But, there's only 2 options, a 1 or a 0. So it's a simple 15 choose whatever question. Here's a much harder question. So in the videos, I specifically talked about strictly increasing sequences or strictly decreasing sequences. Today we have a set A equal to 1, 2, 3, 4, 5, 6, or 7, and we want to choose 3 numbers to form just a decreasing sequence. So 6, 4, 4 is decreasing because the next number is 0 or some positive number less than the previous one. So this is the same thing as choosing 3 with repetition. So this is like saying that 6 plus 3 minus 1 choose 3. This is just equal to 8 choose 3. Because we're just doing combinations with repetition. So, why is this? Well, because let's take a look here. Let's say we want 6, 4, 4. Well, this is going to be the same thing as choosing 4, 6, 4. Okay. And this is the same thing as choosing 4, 4, 6. So when we pick our 3 numbers, we just order them so that they're not decreasing. So that they are decreasing. So that's just the combinations with repetition. And this should be 7 plus 3 minus 1. So that's 9 because we're dealing with 7 elements here. So we have 7, we choose 3, we subtract 1, and choose 3. 7 plus 3 minus 1 choose 3 is the same thing as 9 choose 3. Okay. Question E, I put probably the very first question you ever did with counting as the last one, as kind of like a breather. So how many 6-digit license plates can we make if the first and third digits have to be odd? So we have a 6-digit license plate here. These ones have to be odd, and the 5th digit has to be even, and these other ones can be any number. Okay, because it's 6-digit, so the rest can be any. Well, how many odd numbers are there? There's 1, 3, 5, 7, and 9, so that's 5. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, so there's 10 choices there. Odd we know is 5, any is going to be 10 choices. For even, we have 2, 4, 6, 8, and 0, so that's 5 options. And for any, we have 10 options. So this is the same thing as saying 5 cubed times 10 cubed. So, pretty straightforward. I decided not to put any letters in there because nobody likes to count letters. Okay, so that is the counting questions, the basic ones. I was a little bit mean in this one because I picked such a terrible word. Suppose we have the word parappa the rappa. So how many different arrangements are there if all the letters are distinct? So this means we have how many letters? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 letters. And they're all distinct, so we can arrange them in 15 factorial ways. We can pick any of the letters for the first, any for the second, any for the third, so on and so forth. Okay, how many arrangements are there if the letters are not distinct? Okay, so we should probably sort these. So we have parappa the rappa. So I just sorted all the letters into columns for how many times they're repeated. So we can spell parappa the rappa with these letters. So there's 5 P's, 5 A's, 2 R's, 1 T, 1 H, and 1 E. So if you remember how to do this, this is the multinomial theorem. We have 15 total things. Then we choose 5 P's, 5 A's, 2 R's, 1 T, 1 H, and 1 E. And this is just equivalent to 15 factorial over 5 factorial times 5 factorial times 2 factorial. And 1 factorial is just 1, so we'll leave it out. So the hardest part of the question, I think, was sorting out the letters. And I'm not sorry for that, because, you have to have some challenge other than just writing down numbers, right? No, that's a terrible excuse. Okay, how many different arrangements are there if there are no consecutive vowels? This is much, much more mean. So, if there are no consecutive vowels, so that means that, okay, let's just sort out the consonants here. So we have 5 P's, okay, it's 5 P's, we have 2 R's, we have a T, and an H. Okay, so those are our consonants, and how can we have no consecutive vowels? Well, we have to make sure that they're around all these different letters. So how many spots are there to put our vowels? There's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 different spots to put our vowels. Okay, so what we can do is we can say, let's order the consonants. So how many ways can we order the consonants? Well, 1, 2, 3, 4, 5, 6, 7, 8. There's 9 consonants, so 9 factorial, but there's 5 P's and 2 R's. So much like we just arranged all the letters in the last question, now we only want to arrange the consonants. Now, how many vowels are there? Well, there's 6 vowels, and we want to put them in one of these spots. So there's 10 spots, and there's 6 vowels, so we're going to choose 6 of these 10 spots to put vowels in. So this is where we put the vowels. And then, once we put in the vowels, we have to see how many ways we can order them. So there's going to be 6 factorial ways to order the vowels, but we have 5 A's and 1 E, so we're going to divide by the amount of A's they have, so it's 5 factorial. So this is then arranging the vowels. So this is a 3-part question. You have to order the consonants, you have to put the vowels in their positions, and then you have to arrange the vowels. So a little bit more in depth, but I also believe I might have covered this style of question. Not entirely sure, but some of these questions have to stretch your mind, so I hope that this did that. All right, time for the final question. Here's some questions that relate to combinations with repetition. So we have some integer solution questions. So we have x1 plus x2 plus x3 plus x4 plus x5 is equal to 17, and all of these x's are greater or equal to 0. Well, this is the same thing as saying, okay, we have 17 objects, we have to put them into 5 bins, so we need to get 4 dividers in there. So you can look at it that way, or you can remember that if you have x1 plus x2 all the way up to xn is equal to k, then that's the same thing as n plus k minus 1 choose k. So that's a nice easy way of looking at it. So this will be the same thing as 5 plus 17 minus 1 choose 17. If you need a more in-depth explanation of why this works, definitely check out the combinations with repetitions video. It was a redone video that I did much better, and it's really going to help you with that. Okay, how many integer solutions are there to the same question if x1 and x2 have to be greater or equal to 3, and x3, x4, x5 have to be greater than 0? Well, let's do some changing here. First of all, x3, x4, x5 greater than 0 is actually the same thing as saying x3, x4, x5 have to be greater or equal to 1. So, tricky there. Now, what do? Well, we need to shift these numbers to 0 somehow. So we're going to define some new variables. We're going to have x1 prime. Actually, you know what? Let's call this y1. So y1 is going to be x1 minus 3. So whatever the value of x is, we're just going to shift it over 3. And y2 is going to be x2 minus 3. y3 is going to be x3 minus 1, because we need to shift x3 over 1. y4 is going to be x4 minus 1. That's a y. What am I doing? x4 minus 1. And then y5 is going to be x5 minus 1. So let's substitute this in here. Okay, x1 becomes, well, we need to isolate x1. So we get y1 plus 3 is equal to x1. So we'll do some substitution in here. So our result is going to be y1 plus 3 plus y2 plus 3 plus y3 plus 1 plus y4 plus 1 plus y5 plus 1 is equal to 17. So we'll collect all of our like terms. So we'll get 3 plus 6 plus 7 plus 8 plus 9. We'll subtract it from the right side. So we get y1 plus y2 plus y3 plus y4 plus y5 is equal to 8. And we know that's the same thing as saying 12 choose 8. So a little bit more involved, but I have this exact same example in the combinations with repetition video as well. So this might make a little bit more sense if you go through that video slower. Okay, C and D are the exact same questions with different numbers. So suppose I have 13 textbooks that I want to place on 3 shelves. So we have shelf 1, 2, and 3. How many ways can I arrange my textbooks if order does not matter? Okay, well these shelves are pretty much x1, x2, and x3. And these have to total to 13 textbooks. So x1 plus x2 plus x3 is equal to 13. There's no restrictions, so our x's are greater or equal to 0. So this is the same as saying 15 choose 13 by combinations with repetition. Now, I want at least 2 textbooks on each shelf. Okay, so if substitution didn't make sense before, allow me to explain it visually with this example. So we have 13 textbooks, so we have 13, but each shelf has to have at least 2. So we're going to put 2 on the first one, 2 on the second one, 2 on the third one. Okay, so how many textbooks do we have left to fill in the rest of this space? Well, we had 13, but then we put 2 on the first shelf, 2 on the second shelf, 2 on the third shelf. So now we have 7 left over. So that means that x1 plus x2 plus x3 is equal to 7, because we only have 7 left to put on the 3 shelves, because we just put 2 on x1, x2, and x3. So this is going to be the same thing as 9 choose 7. Okay, that was the midterm. So let's just go over some of the scoring here. So A cross B, A union B, A and B, you should have gotten those hopefully. B minus A, this one might have been kind of tricky for people because it's sort of a trick question. The power set of B, hopefully you got as well. So ideally 8 out of 10 for the first question would be nice. The second question, some people might have challenges with this. I know on midterms you see with solution keys and averages from universities, people tend to not do so well in this question in a Discrete Math 1 course. So some of you might have got like 2.5 on this. because I assume that most people would at least write this if they were stuck. So 2.5 on that. The Venn diagram question, I really hope most of you guys got that right. The statement questions, as I said before, 3 out of 5 would be appropriate. The truth table question, if you're doing any logic, I really hope that truth tables are like your strongest part of logic, because it really is the simplest part of any logic chapter. So hopefully you did get this right. If not, that's okay. You just need to do a few more practice questions and you'll get it. Question 6. Oh god, this one would be terrible. So here's the thing. If you screw up the sentences, you will screw up the result. So, at least 2 out of 10 for writing out some formalizations. That's what I would expect at least. The counting questions, I would really hope, you get A right, you get B right, you might screw up with C a little bit. D might be pretty challenging if you haven't seen my video, and E would be straightforward, so maybe 6 out of 10 on that. Parappa the Rappa, 2 points for 15 factorial, not that bad. The arrangements, if you want a point breakdown for this, really, it's kind of an all or nothing question. And the reason I put 4 points is because I needed to make it worth something more than 2, and I couldn't justify giving only 1 point for the previous question. This next one's a lot more involved. You would get 1 for this one, and 3 for these two. More specifically, this one would be worth 2, and this last one would be worth 1 point. So that would be a total of 4 points right there. Combination with repetition. This first one should be a given. This second one might be challenging. There would be 2 points for doing the substitution in some way. So as long as you showed this would be 2 points, and the answer would be 1 point. And for the shelves, 15 choose 13 would be 3. And this substitution right here would be worth 2 points, and this 9 choose 7 would be worth 1 point. So that's the breakdown, specific question by question. And let's take a look at what your mark would be. So essentially, when I said at least, was that 6, 2.5, 5, 5, 5, 2, 6, 6, 6, something like that would be your average, hopefully. So 6, 8.5, 13.5, 18.5, 23.5, 25.5, 31.5, 36.5, 43.5. Hopefully you can do just that, which would be approximately 62.8%. I might be off, I just did that in my head as whatever. Doesn't really matter what it is. But 62.8%, that would be a B minus if you were the course, if you were the people that I took, if you were the class that I took this course in, and if you were the class that, very similar to this midterm, did this, that would be a B minus mark. So I might have different numbers on my written guide. Follow those. I don't know. Just aim high. That's all I can say is aim high. So that was the Discrete Math 1 midterm. If you have any questions, leave them in the comments below, or leave them on the subreddit, reddit.com/r/TrevTutor, or you can visit the website at TrevTutor.com for some more midterms, and there's also more ways to contact me there. So check it out, and that was the midterm.